You clicked because you heard about a 16-byte x86 instruction that turns matrix rain into sound. That claim is the hook that brought you here, and it is the problem we must solve today. The reality is that no such instruction exists in the available code bases, and the evidence shows that legacy x86 projects use 250 to 700 bytes just to render the visual effect on a screen. But this missing piece of the puzzle is actually more important than the code itself, because it reveals the fundamental architectural shift from scalar logic to the massive parallelism that powers modern artificial intelligence. Let us start with the code you likely saw referenced. The most famous implementations of the matrix digital rain effect on x86 architecture, such as the project by Code Exclusive or the work by Jitu4n, are strictly visual. They rely on direct video memory access at segment 0B800H or VGA registers to draw characters on a terminal. These programs require 250 to 700 bytes of assembly to manage the state of falling characters, the random number generation for the glyphs, and the timing loop that drives the animation. There is no audio synthesis capability in these specific repositories. The idea that a single 16-byte sequence can generate sound from this aesthetic is a fabrication or a misunderstanding of how the demo scene operates. Here is the thing. Even though the audio claim is false, the visual effect serves as a perfect metaphor for the transition we are witnessing in hardware engineering. The matrix rain effect demonstrates what happens when you force a general-purpose central processing unit to simulate a complex system using scalar logic. In a legacy x86 CPU, the processor executes instructions one at a time. It reads a value, performs an operation, and writes the result. To create the illusion of a matrix falling, the CPU must run a loop that updates the position of every single character on the screen sequentially. It processes one pixel, then the next, then the next. This is an instruction-centric approach where the software must manually manage the flow of data through the hardware. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Now consider this. The claim that a tiny 16-byte loop can drive a massive visual effect highlights a critical engineering trade-off. To achieve such a small footprint, the code must be extremely optimized and stripped of all abstraction. It forces the CPU to repeatedly execute the same few instructions to simulate a complex pattern. This is the opposite of how modern artificial intelligence accelerators work. When we talk about GPUs or TPUs, we are talking about tensor processing units designed for data-centric architecture rather than instruction-centric logic. The difference is not just in speed, but in the fundamental way data is handled. A legacy CPU treats the matrix rain as a sequence of events. It calculates the position of character 1, then character 2, and so on. This serial processing is efficient for a small number of tasks but becomes a bottleneck when the data grows. In contrast, a modern GPU or TPU does not calculate one character at a time. It ingests an entire matrix of data and applies a single operation across the entire dataset simultaneously. This is the essence of parallelism. Instead of a loop in software, the loop is built into the hardware itself. This shift from scalar to parallel processing explains why your own projects might struggle when you move from a laptop to a cloud instance. You might be writing code that looks efficient on a standard x86 processor, relying on loops that work well for small datasets. But when you try to train a neural network or process large datasets, those same loops become a bottleneck. The CPU is still trying to process data point by point, while the accelerator is sitting idle because the data is not being fed to it in the right format. The hardware is designed to stream terabytes of matrix data through fixed, highly parallelized arithmetic units, making the software loop the bottleneck rather than the solution. The demo scene technique of compressing logic into a tiny footprint mirrors the difference between these two worlds. The 16-byte demo achieves its effect by strictly serializing logic into a repetitive loop that a CPU executes one instruction at a time. True AI accelerators rely on massive parallelism and data locality to process entire matrices simultaneously. This is why the specific claim of a 16-byte sound generator is misleading. It suggests that you can achieve massive computational power through code compression, but in reality, the power comes from the hardware's ability to handle data movement overhead that the demo bypasses entirely. The transition from the 16-byte scalar loop to modern AI processing illustrates the shift from instruction-centric to data-centric architecture. While the demo forces the CPU to repeatedly execute the same 16 bytes to simulate a matrix, AI accelerators are designed to stream terabytes of matrix data through fixed, highly parallelized arithmetic units. This makes the loop the hardware itself rather than the software logic. The ability to compress logic into a tiny footprint requires extreme manual optimization and a lack of abstraction, whereas modern AI infrastructure sacrifices code density for throughput. It uses massive memory bandwidth and specialized hardware to handle the data movement overhead that the 16-byte demo bypasses entirely. This is the insight that matters for your career. If you are a junior engineer learning production-grade development, you need to understand that the efficiency you see in a 16-byte assembly routine is not a pattern you should replicate for AI workloads. The efficiency there comes from the constraints of the hardware, not from the algorithm itself. Modern AI requires you to think in terms of data movement and parallel execution, not just code density. You must design your algorithms to feed the massive parallel engines of GPUs and TPUs, not to squeeze logic into a tiny loop that a single core can chew through. The lack of any source linking a 16-byte x86 instruction set to sound synthesis challenges the core of the proposed narrative, requiring us to pivot from a technical proof of concept to a conceptual comparison of how legacy scalar logic handles sequential visual updates versus how modern parallel architectures handle massive matrix multiplications. By understanding this distinction, you can avoid the trap of applying legacy optimization techniques to modern AI problems. You will stop trying to write code that mimics the constraints of a 1980s CPU and start writing code that leverages the massive parallelism of the hardware you are actually deploying on. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.